Think about empty space. What is it? You probably picture nothing, a void, a black, silent vacuum between planets and stars. For most of human history, that's exactly what we thought it was: a stage, a background. The things in the universe moved around on this stage, but the stage itself was just there. It was fixed, absolute, and empty. But that picture is wrong, completely wrong. One of the biggest ideas in modern physics is that empty space is not empty at all. It's not calm, and it's not a stage. It's a dynamic, seething, chaotic place. At the very smallest level you can imagine, far smaller than an atom or a proton, space itself is a storm of activity. A bubbling, frothing, unpredictable mess. This idea has a name. It's called quantum foam. And the story of what it is and whether we're part of it is the story of a deep conflict at the heart of science. It's about what happens when our two best theories of the universe collide. To understand the foam, you first have to understand the two ideas that create it. These are the two pillars of modern physics. On one side, you have Albert Einstein and his theory of general relativity. On the other, you have the strange world of quantum mechanics. These two theories are incredibly successful. They are also completely incompatible. Let's start with Einstein. General relativity is the theory of the very big. It's about stars, galaxies, black holes, and the shape of the universe itself. The core idea is simple and beautiful. Einstein realized that space and time are not separate things. They are woven together into a single four-dimensional fabric. He called it space-time. And this fabric isn't just a background. It can bend. It can stretch. It can ripple. What causes it to bend? Mass and energy do. Think of a bowling ball on a trampoline. The heavy ball creates a dip in the fabric. A marble rolling nearby will be drawn into that dip. It will circle the bowling ball. From the marble's perspective, it's just moving in a straight line. But the space it's moving through is curved. That curvature, that dip in the fabric of space-time is what we feel as gravity. Gravity isn't some mysterious force pulling things together. It is the shape of space-time itself. The Earth orbits the Sun because the Sun is a massive object that creates a huge dent in space-time. The Earth is just rolling along inside that dent. It's a powerful idea, and it works perfectly for describing the universe on a large scale. Space-time, in Einstein's view, is a smooth, continuous, gently curving sheet. Now, let's look at the other pillar: quantum mechanics. This is the theory of the very small. It's about atoms, electrons, photons, and all the other fundamental particles that make up the world. And if general relativity is elegant and geometric, quantum mechanics is bizarre and probabilistic. The most important idea in quantum mechanics, the one that gives birth to the foam, is the Heisenberg uncertainty principle. Werner Heisenberg figured out that there's a fundamental limit to what we can know about a particle. You can know its position, where it is, and you can know its momentum, where it's going and how fast. But you can't know both with perfect accuracy at the same time. The more precisely you measure a particle's position, the less you know about its momentum. And the more precisely you measure its momentum, the less you know about its position. It's not a problem with our measuring devices. It's a fundamental feature of reality. The universe is just built that way. It's inherently fuzzy. This uncertainty doesn't just apply to position and momentum. It also applies to other pairs of properties. The most important one for our story is the relationship between energy and time. The uncertainty principle says you cannot know the exact amount of energy in a system for a very short period of time. This has a strange consequence. For an extremely brief moment, the law of conservation of energy can be bent. And it means that for a tiny fraction of a second, a bit of energy can appear out of absolutely nowhere. It can be borrowed from the vacuum as long as it's paid back, almost instantly. What does this borrowed energy do? According to Einstein's famous equation, EMC2, energy and mass are two sides of the same coin. Energy can become matter. So this borrowed energy can pop into existence as a pair of particles. A particle and its antiparticle. They exist for a fleeting instant, and then they annihilate each other, paying back the energy they borrowed. They vanish back into the nothingness from which they came. These are called virtual particles. They are constantly flickering in and out of existence everywhere, all the time. The vacuum of space, the emptiness, is actually a frantic soup of these phantom particles. Empty space isn't empty. It's fizzing with potential. So now we have our two theories. General relativity tells us that space is a smooth, continuous fabric. Quantum mechanics tells us that on small scales, everything is fuzzy, uncertain, and fizzing with borrowed energy. For a long time, this wasn't a problem. Physicists used relativity for big things and quantum mechanics for small things. They lived in different worlds. Gravity is so weak on the scale of atoms that you can just ignore it. And the quantum fuzziness is so small that you can't see it on the scale of planets and stars. But what happens when you try to put them together? What happens when you look at something that is both incredibly small and incredibly massive with a huge amount of gravity? Things like the singularity at the center of a black hole or the state of the entire universe in the first instant of the Big Bang. To understand those, you need a theory that combines both. You need a theory of quantum gravity. We don't have a complete theory of quantum gravity yet. It's the biggest problem in physics. But in the 1950s, a brilliant physicist named John Wheeler started thinking about what such a theory might imply. He asked a simple question: what does the uncertainty principle do to spacetime itself? If quantum mechanics says everything is fuzzy and uncertain at small scales, why should spacetime be any different? But Einstein saw spacetime as a smooth sheet. But what if you zoomed in, way, way in? What would that sheet look like? Wheeler's conclusion was startling. He said that if you could zoom in to an unbelievably small scale, the smooth fabric of spacetime would break down. The uncertainty principle would take over. The geometry of space itself would start to fluctuate wildly. It wouldn't be smooth at all. It would be a chaotic, bubbling, roiling mess. This is quantum foam. Imagine you're flying in an airplane high above the ocean. From your window, the surface of the water looks perfectly smooth, almost like glass. That's the universe as described by general relativity. It's the large-scale view. Now, imagine you're in a tiny boat on that same ocean. You're tossed around by waves. You see the chop, the spray, the bubbles. The surface is anything but smooth. It's a chaotic, energetic place. That's the universe at the quantum scale. The quantum foam is the ultimate close-up view of space-time. At this level, the distinction between space and time becomes blurry. The geometry is constantly changing. And tiny bubbles of space-time inflate and collapse. Tiny wormholes, little tunnels connecting different points in space and time, might momentarily flicker into existence and then vanish. Miniature black holes could pop into being, only to evaporate almost instantly. This all happens on a scale that is almost impossible to comprehend. It's called the Planck length. The Planck length is about 1.6 times 1035 meters. That's a decimal point followed by 34 zeros and then a 1. To give you some perspective, if you were to scale up an atom to be the size of the entire observable universe, the Planck length would be about the height of a single tree. It is the fundamental pixel size of reality. Below this scale, our concepts of space and location simply stop making sense. The time scale for these fluctuations is just as small. It's called the Planck time. This is the time it takes for light to travel one Planck length. It's the shortest possible unit of time. The universe is a frenzy of activity at this level, with space-time itself twisting and churning on a moment-by-moment basis, where each moment is a Planck time. So, to answer the first question, what is quantum foam? It's a theoretical concept describing what space-time might look like at the smallest possible scale. It's the result of applying the uncertainty principle of quantum mechanics to the fabric of space-time from general relativity. It is a reality where space is not a smooth backdrop, but a chaotic, probabilistic, and ever-changing froth of virtual particles, tiny wormholes, and fluctuating geometry. Now, for the second, more personal question, are we floating in it? The answer is yes. But not in the way you might think. We are not like a rubber duck floating in a bathtub full of foam. It's more profound than that. The foam isn't something in space. The foam is space. At its most fundamental level, the very fabric of reality that you exist in is this chaotic froth. Think back to the ocean analogy. We are not tiny boats being tossed around by the waves. We are like massive cruise ships. We are so enormous compared to the scale of the foam that we don't feel its effects at all. The tiny, frantic bubbles and ripples of the foam average out. From our perspective, the surface is perfectly flat. The cruise ship is so large that it glides over the tiny chop without even noticing it. Its own inertia smooths out the ride. Everything we see, everything we are made of, from the atoms in our bodies to the light from distant stars, is a large-scale phenomenon. The particles that make us up are like collections of cruise ships. Their quantum nature is still there, but it's averaged out over a scale that is trillions and trillions of times larger than the Planck length. So, yes, we are floating in it. Or, more accurately, we are made of structures that exist on top of it. The stable, predictable, classical world we experience is an emergent property. It arises from the statistical averaging of this insane underlying quantum chaos. The ground beneath your feet feels solid. The space you move through seems empty and calm. But this is an illusion. It's a high-level view of a low-level reality that is anything but solid or calm. The foam is the ultimate foundation. It's the substructure of everything. The laws of physics as we know them, the very notion of a stable past and future, of cause and effect, might just be the macroscopic consequence of this roiling microscopic foam. This all sounds like science fiction. And in a way it is. It's on the farthest frontier of our understanding. Which leads to the most important question of all. Is it real? Is there any evidence for quantum foam? This is where things get tricky. The honest answer is we don't know for sure. Quantum foam is a prediction, a logical consequence of trying to merge our two best theories. But it is incredibly difficult to test. The scale is just too small. We can't build a microscope powerful enough to see the Planck length. That would require an amount of energy equivalent to the Big Bang, concentrated into a single point. It's not going to happen. So physicists have to be clever. They have to look for indirect evidence. They look for tiny, subtle effects of the foam that might accumulate over vast distances or long periods of time. One of the most promising ideas involves looking at light from very distant objects. Think about light that has traveled for billions of years from a distant galaxy or a quasar. If spacetime is a perfectly smooth fabric, like Einstein imagined, then that light should travel unimpeded. But if spacetime is foamy, if it's a chaotic mess at the smallest scales, then the light's journey would be different. A photon of light traveling through the quantum foam would be like a person trying to walk a perfectly straight line on a shaky, vibrating floor. The tiny jitters in space-time would affect the photon. Over a journey of billions of light years, these tiny effects could add up. Some models of quantum foam predict that the foam would affect different colors of light slightly differently. High-energy photons, like gamma rays, have shorter wavelengths. They would be more sensitive to the tiny bumps in space-time. Lower-energy photons, like radio waves, have longer wavelengths and might skim over the foam more easily. This means that if a burst of light containing all different energies was released from a distant cosmic event, like a gamma ray burst, the photons might not all arrive at Earth at the same time. The high-energy gamma rays might be slightly delayed, having been jostled more by the foam. Astronomers have used powerful instruments like the Fermi Gamma Ray Space Telescope to look for this effect. They have observed gamma ray bursts that have traveled for billions of years, and the results so far? They haven't found any delay. The photons all seem to arrive at the same time, regardless of their energy. This is a bit of a disappointment for supporters of the foam idea, but it doesn't kill the theory entirely. It just rules out some of the simpler models of quantum foam. It tells us that if the foam exists, its effect on light is much smaller than some theories predicted. The universe, it seems, is smoother than we might have thought, even when we look for these tiny effects. The search continues, with scientists looking for even more subtle signatures. There is another piece of evidence, though it is very indirect. It supports the idea behind the foam, if not the foam itself. It's called the Casimir effect. This is a real measured phenomenon. If you take two perfectly smooth, uncharged metal plates and place them extremely close together in a perfect vacuum, something strange happens. They are pushed together. A force appears out of nowhere. Why? The explanation comes from the world of virtual particles. Remember them. The little particles that pop in and out of existence everywhere in the vacuum. Outside the two plates, virtual particles of all wavelengths can exist, but the tiny gap between the plates restricts them. Only virtual particles with wavelengths that fit neatly into that gap can pop into existence there. This means there are more virtual particles pushing on the outside of the plates than there are on the inside. The result is a net pressure, a tiny force pushing the plates together. The Casimir effect has been measured in labs, and it matches the predictions of quantum theory perfectly. This is a stunning result. It is direct experimental proof that empty space is not empty. The vacuum has energy. It is a dynamic, active place. And since the activity of the vacuum is the engine that drives the theoretical concept of quantum foam, the Casimir effect provides strong, if circumstantial, support for the underlying physics. It shows us the vacuum is alive. So where does that leave us? We are living on top of a theoretical foundation of reality that is a chaotic, bubbling mess. And we can't see it, we can't feel it. Our best attempts to measure its effects have so far come up empty, though we have proven that the vacuum itself is not empty. The idea of quantum foam remains one of the most compelling and most frustrating in all of science. It's what you get when you take your two best recipes for the universe and try to bake them into one cake. The result seems to be this strange frothy substance, but we can't taste it to be sure. If quantum foam is real, the implications are profound. It would mean that reality is not continuous. It's pixelated. The universe is, in a sense, digital. The Planck length is the size of the ultimate pixel. You can't have half a pixel. It could also change our understanding of the universe's biggest mysteries. For example, there's a huge problem in cosmology related to the energy of the vacuum. When physicists try to calculate the amount of energy that should be in the quantum foam based on all those virtual particles, they get a number that is staggeringly large. It's 10,020 times larger than the energy density we actually observe in the universe. If the vacuum had that much energy, its gravitational effect would be enormous. It would have blown the universe apart instantly. The fact that we are here in a relatively calm and slowly expanding universe means our calculation is catastrophically wrong. This is often called the worst theoretical prediction in the history of physics. Something is canceling out all that energy, we don't know what. A full understanding of quantum foam, as part of a theory of quantum gravity, would have to solve this problem. That should explain why the vacuum is so much less energetic than we think it should be. And what about the beginning of everything? Where did the Big Bang come from? Some speculative ideas suggest that our entire universe could be just one bubble in an eternal, infinite quantum foam. A random fluctuation a bit larger and longer lasting than most could have provided the seed energy for our entire cosmos. In this view, universes could be bubbling into existence all the time, part of a much larger, timeless multiverse of foam. This is speculation, of course. We are a long way from proving any of it. The search for a theory of quantum gravity continues. Theories like string theory and loop quantum gravity are different attempts to build that bridge between Einstein and the quantum world. They each have their own, slightly different pictures of what space-time looks like at the Planck scale. String theory suggests it's made of tiny, vibrating strings. Loop quantum gravity describes it as a network of interconnected loops. But they all share a common theme. The smooth, continuous space-time we know is an illusion. The ultimate reality is something discrete, granular, and fundamentally quantum. So, we live in this strange state of knowing and not knowing. We are floating. We are existing. Our every moment is supported by a bedrock of reality that defies all our everyday intuition. It's a reality that is not solid, not empty, and not calm. It is a place of pure potential, a sea of possibilities flashing in and out of existence in moments too brief to measure. The smooth world you see around you is just the surface. It's the average. It's the cruise ship's placid journey. But underneath it all, at the very bottom of what it means to be a place or a time or a thing, there is the foam. A storm of pure creation and destruction, from which the solidity of our world somehow emerges. We may never see it directly, but it is always there. The shaky, uncertain, and wonderful foundation of everything.